So I'd like to use the next half hour, 25 minutes, to discuss recent advances in silicon nitride integrated photonics. And so first of all, I regret I cannot be here in person, but I'm happy that I actually had the opportunity to give this presentation in this hybrid format. And so what I want to do is give you kind of an overview talk of work that we've been doing in my lab at EPFL for the last 10 years or so on a novel kind of integrated photonic platform that is based on silicon nitride. And I'd like to walk you through some of the advances that we made in the last kind of years and kind of highlight the opportunities, in particular for quantum science, actually, as we go forward to the future. So let me start out by also acknowledging kind of our funding agencies that, of course, are indispensable kind of for this work, and also the co-workers, which I'll mention here at the end. Okay, so let me get started by introducing to you very briefly kind of some of the motivational work for what I'm going to talk about. And that is an enduring challenge in integrated photonics, that is to achieve low loss. So let me mention the very reason actually I can give this talk today here is due to the pioneering work of Charles Kao, who developed ultra low loss fibers back in the 70s, and understood kind of that what the impurities, what the limitations were, in particular kind of metal impurities and OH. And today optical fibers have achieved a remarkable kind of level of loss of less than 0.2 dB per kilometer, and allow kind of transcendental communication, and really backbone of optical information society. And evidently for this groundbreaking work, this was also recognized by the Nobel Committee in 2008. Now, if one looks at a different field, that of integrated photonics, what's kind of striking is that despite major advances of integrated photonics and even commercial products that are being fabricated in kind of billion-dollar kind of state-of-the-art silicon foundries, such as Global Foundries, TSMC, today still integrated photonics, up to about a decade ago, could still only obtain losses on a level of 1 dB per centimeter. So there's a 5 orders of magnitude discrepancy between optical fiber communications and what can be done today in integrated photonics. Now, what I'm going to talk about today is actually has been an effort in my lab, but actually many other labs around the world, to really break that the barrier. And I'll show you examples now where in integrated photonics, we cannot obtain what you can obtain in fibers, but we can obtain losses that are now on the level of dB per meter. And these actually values are rapidly advancing. Now, this is not purely an academic endeavor. In fact, there are new applications that are enabled by this ultra low loss that I'd like to highlight today. So first of all, what is the material that I'm going to talk about today? It's silicon nitride. And silicon nitride actually has a number of appealing advantages when it comes to integrated photonics. But strikingly, it's only been in the last 10 years that these advances have been explored. So the first is that compared to silicon, actually, you have a band gap of 5 electron volts. So it can guide light in the visible. And that's particularly interesting to make visible integrated photonics, which I'd like to briefly also talk about today. The transparency window also extends to the mid-IR, so it can generate even mid-infrared frequency chromes up to 4 micron. It has very high optical power handling. In fact, these materials we've shown can handle up to more than 1 watt, actually up to 10 watts of optical power in a nanophotonic waveguide with a micron square diameter. And that's in contrast to silicon, where typically 2-photon absorption limits the optical power handling. And this is, of course, important for this talk, I'll show you advances where we've really taken kind of the level of losses of a dB per centimeter that's conventional, even in state-of-the-art kind of, global foundry silicon photonics, down by a factor of 100 to 1 dB per meter. And this enables novel applications that I'd like to tell you, in particular, actually, in optical frequency comb generation, but also in quantum frequency conversion, as well as lasers for the visible, in particular for quantum technologies. Okay, now, so brief kind of history of silicon nitride. The material is well known in CMOS industry. It's been used as end-cap layer or edge stop in CMOS for many years. There's an early attempt in the 70s already to use this material for integrated photonics, but these have typically been compounded by optical losses and the difficulty of achieving thick silicon nitride films. Thick because the material, when grown using low pressure chemical vapor deposition, tends to form cracks. Now, this in really some groundbreaking work from Michael Lipson in 2008 was shown to be possible to overcome. So this showed actually for the first time that you can make kind of nonlinear devices in silicon nitride with decent quality factors. And in our lab at EPFL demonstrated a novel process, the Damascene process, that brought down the losses from this early work by almost 2 orders of magnitude, allowing dB per meter length scale integrated photonics And it's also a process that we commercialize with our startup Ligentech that's now 6 years old, and it's serving kind of the integrated photonics community with silicon nitride chips. Now, silicon nitride, as mentioned, has been explored in a variety of forms. What I'm going to talk about today is mostly really the high confinement waveguide technologies. So high confinement means here that the light actually is fully confined in a silicon nitride film, and this is to be contrasted to low confinement waveguides, which have been studied for an extensive amount of time, more than already a decade ago. But these confinements low confinement implies that one cannot take advantage of some of the nonlinear properties of silicon nitride. So silicon nitride, and I will not go into detail, but I want to mention that over the last 10 years, there's been a lot of progress actually on making this kind of a new platform for negative photonics. We and others have demonstrated that the platform can be combined with lithium niobate, opening a perspective of also utilizing the Puckles effect for fast electro-optic modulation or quantum frequency conversion. You can also achieve heterogeneous integration of 3-5 materials, in particular 3-5s that allow to obtain kind of also amplification and laser action on the same kind of silicon nitride die. You can include piezoelectric modulation via combining with MEMS technology, and also integrate detectors in the same kind of platform. And so today we have a growing maturity of the silicon nitride platform that really establishes it in parallel to the well-developed silicon platform that's available today. Okay, so what are the application of these tightly confining silicon nitride integrated photonic waveguides? So today I want to highlight a few of them. I want to talk about the ability to generate optical frequency combs, which is possible by exploiting so-called dissipative Kara-Salt information. A recent avenue is the ability to use this platform to create integrated lasers that are frequency agile and have low phase noise. And here there's been very recent advances from my lab and also lab from Vahala and Bowers that has shown that we can not only make lasers that have a compact form factor, but in fact we can demonstrate that we have lasers whose phase noise is on par with the phase noise of fiber lasers, which is considered the workhorse of fiber sensing. And so it's the first time that integrated photonics not only achieves compact form factor, low power consumption, but really achieves a fundamentally improved phase noise and frequency tunability compared to legacy laser systems. And that's in particular interesting for addressing visible wavelengths that I'll briefly touch upon. You can also generate parametric amplifiers. You can use it for linear optics, for supercontinuum mid frequency comb generation, or combine it with lithium niobate to make a platform for a heterogeneously integrated lithium niobate for modulators or frequency converters. And in very recent work, we've also demonstrated that this low-loss platform can be endowed with further functionality, such as optical gain from rare earth ions, and erbium is one key example. And we have forthcoming work actually coming out tonight that shows that we can obtain state-of-the-art amplification in silicon nitride waveguides on par with fiber amplifiers by combining it with ion implantation. And this really opens the door to make fiber lasers on chip or to make mode-lock femtosecond lasers fully chip integrated for frequency metrology applications and optical clocks, as one example. Also, integrated photonics is finding use in very different fields that are non-traditional. One non-traditional field is that of electron microscopy. And here, with a group of Klaus Robers, we demonstrated that integrated photonics allows continuous beam electron phase modulation to be achieved. And this is a new area where integrated photonics can be used for electron beam control. Okay, so what are some of the salient features for silicon nitride for nonlinear optics? For nonlinear optics, its key advantage is that it has a high band gap of 5 eV, so there's no two-photon absorption. And the material also has a very large ratio of the Kerr-to-Bruin nonlinearity. And that implies one can propagate very high powers in the waveguides without suffering from stimulated Bruin scattering and explore fully the Kerr nonlinearity in this platform. So a point about the waveguides I'm going to discuss, I'm going to talk about tight confinement waveguides, and I want to briefly motivate why this is interesting. So tightly confining waveguides are waveguides where the optical field is fully confined in silicon nitride or the waveguide core material. And in the case of such materials, if one looks at the effective index as a function of wavelength, one is in a region where most of the field actually is fully confined, in the core. So the effective index is very close to the core effective index, and it's this region actually where the curvature corresponds to basically a group velocity dispersion, okay, that is negative. That is to say that the free spectral range increases with frequency. And this is the region where one inch of anomalous dispersion, which is required when exploring the silicon nitride platform for solid formation or frequency cone generation. Now, very briefly, one of the technical challenges that has plagued the advancement of silicon nitride is the fact that the material is difficult to etch. It's a hard material. It forms it's deposited under very high stress, which promotes the formation of cracks in the waveguides. And this has for a long time precluded the exploration of tightly confined indicator photonics based on this platform. So over the last 5 years, we've developed a new fabrication process called the photonic damascene process that allows reliable crack-free fabrication of really wafer scale, so 100 millimeter wafer scale indicated photonic circuits based on silicon nitride, where for the experts in the audience, we can even place two waveguides, okay, in very close proximity and have no problems with gap filling of SiO2, which are very challenging actually in traditional kind of subtractive manufacturing. And so this new method of this photonic damascene process is based on a well-established kind of idea in copper interconnects and VLSI, which is called the damascene process. And so the damascene process is a process by which you do not etch the material you deposit, in our case silicon nitride, but rather you create reset structures. So you create a reset structure in a silica wafer that you deposit with silicon nitride and afterwards planarize. And this is the exact same process that was used in Damascus already to create these ornaments, except now that we're not using metals as in VLSI, but actually we're using dielectrics. And so this idea can be modified in one very important way, and that is the following. We can also take the preform, which is made from glass, and heat it up to the glass transition temperature, 1200 degrees. And this actually takes out any roughness in the waveguides. And this allows to create indicator photonic waveguides where we have losses that are approaching 1 dB per meter losses, which is about a factor of 100 improvement of what can be done with state-of-the-art silicon photonics indicator photonic circuits. We have shown that the roughness actually in these waveguides is less than 2 nanometer RMS, while still keeping the dimensional accuracy actually of the preform. So silicon nitride actually has even more potential. So we have measured the fundamental absorption loss in the platform, and the fundamental absorption loss actually corresponds to less than 0.15 dB per meter. So there's still a good order of magnitude improvement before we even will reach the fundamental kind of limits actually of these material platforms. Now, so this is an example of some of the devices that we can make today, and just to show you that these are not kind of one-off results, but really results we can now obtain reliably across a 4-inch wafer on every field of the DUV stepper. And so the silicon nitride now has become really a workhorse for a lot of experiments in integrated nonlinear photonics and also emerging applications in the field of quantum science and technology. So what are some of these applications? I mentioned already frequency aerogel lasers, ultra-low loss photonic circuits for modulators, but there are many other applications that are actually not shown here that this can also be used for. Now, reaching out a bit and just highlighting one application in the field of quantum science, I want to mention that there was last year a beautiful kind of publication that came out from Xanadu, a Canadian quantum startup, and they demonstrated a programmable photonic circuits, and in fact the circuit itself, which was shown here in the picture and used in the paper, actually wasn't based on silicon nitride, manufactured at Leichentech, the company we started 6 years ago that commercializes now and democratizes access to this technology. So let me briefly mention some of the applications and kind of novel physics you can access in these traveling or in these silicon nitride integrated circuits. So the first one I very briefly touch is you can make the loss levels have now come so low that one can make and realize a very old idea that has been compounded in the field of fiber optics, and that is one can make traveling wave optical parametric amplifiers. And so what's shown here is a chip 5 by 5 millimeter with two spirals that are 1 meter in length. And again, the losses here are just 1 dB per meter. And in fact, despite the simplicity of the structure, what we can access here is a very beautiful nonlinear optical phenomena, and that is that of traveling wave optical parametric amplifiers. So if one propagates a pump laser that's very strong inside a dispersion engineered silicon nitride waveguide, where we operate very close to the group velocity dispersion 0 point, which we can engineer by the geometry, one can amplify actually the signal. And so one achieves this by using the parametric amplification process, so the Chi3 of the material. And so the idea of using parametric amplification has a very long history in fiber optics, dating back to the 80s. And it's a very compelling way to amplify, because this amplification operates at the quantum mechanical limit of 3 dB for phase insensitive amplifier. And above all, this amplification method here has the advantage of also allowing phase sensitive amplification where the noise figure is 0 dB. Now, it's been very challenging, however, to obtain parametric amplifiers in optical fibers, simply due to the low linearity of the fiber itself and the large cross-section of the fibers. And so there's only been one report back in 2001, almost 20 years ago, with power levels that proved impractical to put into real systems. Interest in this process renewed with the advances in silicon photonics, but net gain actually could not be achieved in this platform, or at least not a net gain that is sufficiently high to really be practical for applications. And we have demonstrated together with a group of Andrickson just very recently in 2021 that in fact we can obtain continuous wave parametric gain actually in such a device. And so what's really compelling actually about this type of amplifier is that in contrast to urban amplifiers, which give gain in a very narrow region between 195 and 198 kind of terahertz, with parametric amplifiers, one can achieve broadband gain. And the gain here is literally just designable by lithography. So what is shown here is a waveguide whose dispersion is engineered in such a way that we operate and knock out higher dispersion terms to get a very flat actually operating amplification window that in this case exceeds far beyond the C and L band used for telecommunications. In fact, one can even move this amplification band down to the visible and create parametric amplifiers that amplify visible light. And so this is really a new way to amplify, and it's a principle that we recently demonstrated. This is an example of our experiments that are forthcoming. Where we send a strong pump together with a signal inside one of our spiral waveguides of 1 meter, and observe in this case more than close to 15 dB of gain in this system due to the parametric amplification process. And so where could this kind of lead in the future? As mentioned and alluded to, silicon nitride still has a lot lower loss than one can realize. And we believe that if one can reduce the losses by another, maybe ideally order of magnitude, say 0.5 or 0.15 dB per meter, then one can see that already with a with a 50 meter length spiral, okay, one can obtain more than 4 dB gain, which is kind of a record compared to also what typical urban doped fiber amplifiers can achieve. And so that's one example of kind of the physics that one access in these silicon nitride devices. Let me briefly highlight another physical principle that we can access in these silicon nitride photonic integrated circuits, and that is optical frequency comb generation. And so frequency combs are really the workhorse of modern metrology. They are an integral part of any optical clock. They allow optical frequency synthesis. They can be used for spectroscopy and many other applications. And they go back to the pioneering work of Ted Hench and Jen Hall. Now, despite kind of 20 years of frequency metrology, this technology is still not ubiquitous. And so only kind of very privileged labs, such as government lab or metrology labs that are well funded, can actually afford to have these self-reference optical frequency combs really being used. And so over the last 10 years, there's been kind of the vision to make chip-scale optical frequency combs. And the same parametric process that I just showed in the last minutes can also be used to generate optical frequency combs by moving to a resonant structure, so by moving to an integrated resonator. And this comb generation using parametric oscillations was first observed, almost 15 years ago in kind of handcrafted glass resonators. And what is interesting about that process is that its threshold goes inversely, with the quality factor, so inversely with the propagation losses, and in a quadratic fashion, and thereby by decreasing the optical losses, one can obtain a dramatic reduction in the pump power required for this Carrier frequency comb generation. So this process not only generates frequency combs, but one can also generate so-called dissipative Carrier solitons. And so it's a physics I will not have the full time to explain, but let me just highlight that when you tune it through the resonance, one can generate a so-called modulation instability pattern. So one has a wave breaking phenomena where one generates a chaotic waveform. And by appropriately stopping the detuning, one can reach a regime where one can promote the formation of dissipative kersolitons. Okay, and so in fact, the system that we're studying, so this resonator driven by CW laser, is described by a so-called nonlinear Schrödinger equation with dissipation, detuning, and a continuous wave drive, and it's known under the name of Legato-Lefevre equation. And this equation has as solutions, okay, both regions where, as a function of the pump power and a function of the detuning of the laser, it admits both solutions where the waveform is chaotic, the waveform can breathe, or the waveform can form stable solitons. And so we can access this two-dimensional phase diagram actually very easily by changing the detuning and the power of the laser. And so the point that we operate in is the one where we can form these kind of dissipative kersolitons with mathematically our solitons that are SESH kind of profile and that lock to a CW background. Now the applications of these dissipative kersolitons actually are very vast. Importantly, one can also generate them in the silicon nitride platform, where they can encompass 2/3 of an octave and where they can be modeled again by this Legato-Lefevre equation. And the applications of these dissipative kersolitons include astrophysical spectrometer calibration, coherent communications, distance measurements, atomic clocks, but also applications such as optical frequency synthesis, OCT, or dual column spectroscopy. And we've explored many of these applications kind of in the last years. And so one example I want to give where these microcombs can actually play a role is in coherent communications, where one can use two of these frequency combs, one on the transmitter side, one on the receiver side, to both encode data in both the amplitude and the phase of the field, and also decode it on the receiver side. And we've demonstrated this actually with the group of Christian Kuz a number of years ago. Another example that is emerging is that for LiDAR, where we use we can use these solitons to make a so-called massively parallel FMCW comb that can be used for instantaneous distance and position measurements of objects. And we've realized this recently, again, using the silicon nitride microcomb kind of approach or technology. Now, last, I just want to briefly in the last 2-3 minutes highlight that the silicon nitride platform can also be made hybrid and combined with other technology. And here we've worked with a group of Sinobave in Purdue for the last number of years to include very fast actuation using the ALN MEMS technology. And so ALN MEMS are used in cell phones for wireless filters. It's a material that has a very high actuation linearity, large bandwidth, no hysteresis, very low kind of leakage current, and it's really wafer scale process. And we have been able to combine this MEMS process with silicon nitride. And so in one go, so in brief, we can include a thin layer of aluminum nitride with actuators on top and bottom. And then via the stress optical effect, by applying a voltage, we actually can change the refractive index of the underlying silicon nitride kind of die, and thereby impart a frequency shift. And this can be quite significant. So we obtain tuning voltages as high as 30 megahertz per volt with actuation bandwidth that can be as high as a gigahertz. And this is distinct and very significantly faster than the typical piezo tuning with bulk lasers that one can obtain, which are typically limited by a few tens of kilohertz. So so we've shown actually that this technology can be used, for instance, to achieve very fast actuation of soliton frequency combs. So where we can actuate an optical comb and very quickly actually change the center frequency. But what we also have changed and demonstrated recently is that this technology can be used to create a new kind of generation of indicated lasers that have ultra low noise and are frequency agile. And these lasers, the way they operate is using a technique called self-injection locking, where we couple our silicon nitride dye with aluminum nitride MEMS to a DFB. And the very large quality factor allows a dramatic collapse actually of the lasing line width and reduction of phase noise by more than 30 dB. If we actuate the device in such a way that we change the operating point within the injection locking region, we can obtain very fast frequency actuation. And we've demonstrated that this actuation can be extended up to kind of hundreds of kilohertz, even megahertz. Which is significantly larger than what can be achieved actually with traditional kind of bulk lasers. What's equally important and even more enticing is the fact that if one looks at the phase noise of these lasers, In fact, the phase noise is only dominated by thermodynamical fluctuations of the silicon nitride cavity volume. And so we can operate these at a thermodynamical limit and reduce the phase noise by decreasing the cavity size. And so those people who are not familiar with the phase noise, let me just mention that the phase noise that we obtain these lasers now is comparable to that of optical fiber lasers, which are the workhorse of fiber sensing, as alluded to earlier. And it demonstrates that these integrated photonic lasers based on silicon nitride are now also overtaking kind of bulk legacy laser systems. One can also move the silicon nitride into the visible, and it's a collaboration result I'd like to show here at the end with Park. Particularly interesting for, say, for the community of people working on optical clocks, which is that in clocks, there's a variety of transition one wants to address. Here an example of the strontium level diagram with a 461 nanometer kind of cooling transition, 689 kind of clock transition. And so all these transitions are typically invisible. And where to date, you have mostly legacy laser systems based on bulk ECDLs. And the silicon nitride platform, which you've shown, can really dramatically miniaturize actually the ability of these visible integrated lasers. And one example we recently demonstrated is self-injection locking. So a frequency tunable low noise laser that operates at a wavelength as short as 410 nanometers. And so this is the shortest wavelength integrated photonic laser that's been demonstrated to date. We can even go a bit shorter in wavelength. And so here's a silicon nitride PIC, in this case a gallium nitride diode for the gain. We can also put aluminum nitride actuators for fast frequency actuation. Comparison to state-of-the-art kind of lasers show that our phase noise already is today lower than commercial lasers that are made for 461 nanometers. And it shows the tremendous potential that integrated photonics has, in fact, to provide lasers also in the visible spectral domain. Now, last, let me mention that the platform that I've described of aluminum nitride can also be used for experiments in the field of microwave to optical frequency conversion. So the same devices that I showed with the ALN can also be used to convert incoming microwave fields to optical photons and vice versa in a bidirectional manner by exploring the coupling to so-called H-bar mode, so high bulk acoustic resonances in the silica slab. In this case, that contains the silicon nitride waveguide. And this kind of structure we've made, and we have actually demonstrated that we can obtain conversion efficiencies as high as 10 to the minus 3 with potential to go to 10 to the minus 3 of converting microwave photons to optical photons using this hybrid electro-optical transducer. So in summary, I'd like to mention that there's many applications of integrated photonics, in particular in conjunction with materials such as lithium niobate, be it in transduction, be it in Chi2, Chi3 nonlinearity, or being in the field of lasers for optical atomic clocks. With this, I'd like to thank you for your attention, and I'm happy to take any questions.